The conductivity of pure germanium or silicon, so-called intrinsic material, is very low. It can be altered by doping the germanium, that is, introducing foreign atoms, atoms other than germanium. What happens if one of these atoms is replaced by an atom of antimony which has 5 valency electrons, each represented here by a single green bar? 4 electrons are absorbed into the lattice, but for the 5th electron there is no place to fit into the bonds. This superfluous electron will, at a temperature of absolute zero, move in a wide orbit around the atom. However, at room temperature, this electron can take so much energy out of the vibrating lattice that it will be knocked out of its orbit and it will be free to move through the crystal. This atom, with its 5th valency electron in close vicinity, is known to be electrically neutral. But when the 5th electron is thermally knocked out of its orbit, then the positive electric charge of the nucleus is no longer neutralized. And as a result, the remaining part of the antimony atom reveals itself as a positive ion. When many germanium atoms are replaced by antimony atoms with 5 valency electrons, then many free electrons will be introduced into the crystal. So at room temperature, there are as many free electrons as there are positive ions. But in germanium and silicon, there are at room temperature free electrons and holes already present, owing to generation. Now the introduction of the antimony atoms brings many extra free electrons into the lattice. It is clear that in a crystal that is enriched with many extra free electrons, a great part of the holes will recombine and only a few holes will remain. Such a crystal is called an N-type crystal. N for negative electrons, which are introduced into the crystal by means of many 5 valency antimony atoms. These atoms are called donor atoms because each donates an extra electron to the crystal. The N-type crystal thus possesses only a few holes and many free electrons, far more than a pure crystal. So if an electric field is applied, there are more charge carriers, more electrons, than in a pure or intrinsic crystal, so that the resulting electric current will be higher. Conductivity is thus increased in this so-called extrinsic material. There is also another way to increase the conductivity of the pure crystal. Suppose we replace an atom of germanium with one that possesses only 3 valency electrons. For example, an indium atom. One bond cannot be filled, thus there will be a shortage of 1 electron. Or, in other words, a hole is introduced by the indium atom into the crystal lattice. At absolute zero temperature, this hole moves in a wide circular orbit around the indium atom, just like the electron in the N-type crystal. At room temperature, there is so much thermal movement that the hole is knocked out of its orbit and moves freely through the lattice. With this positively charged hole in close proximity to the indium atom, this atom is electrically neutral. But without this positive hole, the indium atom manifests itself as a negative ion. If many 3-valency atoms are introduced into the lattice, then there will be many extra holes in the crystal. At room temperature, these holes will be free holes. As is known, at room temperature there are already free electrons and holes in the crystal owing to generation. Now the introduction of indium atoms into the lattice brings many extra holes into the lattice. With this large number of holes, the chances are great that an electron will recombine with a hole and disappear. So it is clear that with so many holes in the crystal, a great part of the electrons will recombine so that only a few electrons are left. Such a crystal is known as a p-type crystal. P-type because holes behave as positive charge carriers. They are brought into the grid by 3-valency atoms. These atoms are called acceptor atoms because they can accept one electron as the hole moves away. If an electric field is applied, then conduction takes place via the many holes that are now present. Thus, the conductivity of a p-type crystal can be made much higher than that of a pure crystal. Analyzing the situation, it is found that pure germanium and silicon are insulators at a temperature of absolute zero. At higher temperatures, there is a certain quantity of holes and electrons, owing to generation and recombination. And now the crystal conducts. At room temperature, it appears that in germanium there are about 10 to the 13th electrons per cubic centimeter, and also about 10 to the 13th holes per cubic centimeter. But still, they give only poor conduction. Now, conductivity can be increased. The germanium crystal can be enriched by a quantity of pentavalent atoms, replacing germanium atoms, and thus increasing the number of free electrons. In this way, the N-type crystal is formed, having many electrons, for example, 10 to the 16th per cubic centimetre, and only a few holes, 1,000,000 times less, namely 10 to the 10th per cubic centimetre. Since there are now 1,000,000 times more electrons than holes, the many electrons are called the majority carriers, or majorities, and the few holes are called the minority carriers, or minorities. On the other hand, by replacing germanium atoms with acceptor atoms with 3 valency electrons, the number of holes increases. In this way, a p-type crystal is formed, having a large number of holes, for example, 10 to the 16th per cubic centimetre, and only a small number of electrons, or 1,000,000 times less, namely 10 to the 10th per cubic centimetre. In the p-type crystal, there are many more holes than electrons. Therefore, here the majority carriers are the holes, and the minority carriers are the electrons. So, with the formation of P and N crystals, higher conductivity can be achieved.